Thank you very much. Thank you for everyone for putting on this conference and speak, and thank you for coming. Yeah, so I should say something about the title before I start. So yeah, so if you're someone who cares deeply about this true complexity problem, which I haven't talked about yet, but I will, then this is great. You're in the right place. If you're someone who don't care about that problem, or you don't know that you care about that problem, then the way you should think about this is that you can sort of choose your own adventure. So I'm going to be telling you about some techniques involving iterated Cauchy Schwarz and like things you can prove by applying the Cauchy Schwarz inequality many times that maybe you think you might not be able to prove to start with. And there's a sort of proof of concept, which is that I can use it to prove this true complexity problem. But if you have another application in mind where you would like to prove something using Cauchy Schwarz techniques, then maybe these techniques will be helpful, and yeah, try and imagine what it is you would apply to. So that's really the way to think about it. Yeah, so what should I say? So okay, if I set up some notation, I'm always going to be using expectation to mean an average over some finite set. A convention that applies throughout this talk is that all functions are bounded by 1 unless I say otherwise. So any function taking values in the complex numbers is 1 bounded. So yeah, just to give an example, I mean, this is an audience of discrete analysts and multiplicative number theorists, so I assume that most of you have applied the Cauchy Schwarz inequality yourselves. But just to make sure we're on the same page, this is sort of what I mean by applying the Cauchy Schwarz inequality multiple times to prove something. So this statement says, yeah, if I have some finite set, I have a function f in 2 variables, then this expression on the left, f of xy of xp of y, is controlled, is bounded by the expression on the right with this complicated pattern of f's and complex conjugates. Okay, so this is a statement, it's true, and there are many ways to prove it. So for example, you can prove this using spectral theory. If you think of f as a matrix and you take its eigenvalues, then you can interpret the left-hand side and the right-hand side in terms of eigenvalues. But you can also prove it purely by hand by applying the Cauchy Schwarz inequality twice. And say, just to make sure we're on the same page, I'll see what that looks like. So yeah, you'd start out with the left-hand side, and then you can sort of rearrange it to notice that, well, if you pull the a out, then a only depends on x, so you can put the y average in with the rest of it inside. And then you can think of this as the inner product of a of x with this other strange function of x, and then apply the Cauchy Schwarz inequality, and you'll get the L2 norm of a and the L2 norm of this other strange thing. And we can ditch this left bit because this is at most 1 and just focus on the right bit. And if you sort of expand this out and then rearrange it, you get an expression that looks like this. So I've doubled up the y. I now have a y and a y prime. I have 2 copies of b, 2 copies of f. But again, I can notice that I can pull the b's out because they don't depend on x. And then what I have left is a function of x with the average on the inside. And then I can think of this as the inner product of this as a function of y and y prime, and this is a function of y and y prime, and I can apply the Cauchy Schwarz inequality. And I'll get the L2 norm of this thing and the L2 norm of this thing. And again, the left piece here is bounded by 1, so I don't care. And the right-hand piece, when you expand out the this inner square and take 2 copies of x, this is exactly what I wanted. So that's equal to the right-hand side. Okay, so I think you'd be forgiven for saying that you don't find this argument terribly fascinating. I mean, you just take this Cauchy Schwarz and see what you get. It is very useful. I mean, you can use this sort of thing to count the number of copies of the Peterson graph in some. So yeah, this stuff comes up a lot. Yeah, I mean, you might also object that maybe I could have done this just using spectral theory and eigenvalues and so forth. Wouldn't that have been easier? Why do I have to sort of be a Luddite and only use Cauchy Schwarz? But there are other situations. So if I have functions in 3 variables rather than 2 variables, then I might have some hypergraph expression that looks like this. So think of f now as like the indicator function of a hypergraph or something. And I want to bound this above by something. And my Cauchy Schwarz argument works just fine. I Cauchy Schwarz out the a's and the b's and the c's, and I get some monstrous expression on the right-hand side, which you can work out if you're bored enough with this talk that you'd rather do that. If I have a different pattern, if I have functions a, b, and c in only 1 variable, and I Cauchy Schwarz this out, then I get some different pattern on the right-hand side, and so forth. And you can, and these things have no known analog in spectral theory. There's no nice spectral theory of tensors. So yeah, so that's very useful. The case I actually want to talk about is a sort of arithmetic version of all this. So this is where I have functions as an arbitrary set, and I'm sort of doing combinatorics and graph theory and stuff. I want to think about where I have functions on an abelian group. So G is going to be my favorite abelian group, which is z mod pz to the n, or fp to the n. In this talk, I'm sort of ambivalent, by the way. You can think of n as being 1 and p being a very large prime if you want, or you can think of p being 7 and n being a very large number. I can handle both of these and anything in between. So again, you can think of whichever example you want. So what's an example of something you prove in this arithmetic setting by applying the Cauchy Schwarz inequality many times? Well, this is a lemma due to Tim Gowers, I guess, or at least explicitly to Tim Gowers, sort of maybe known in spirit before Tim Gowers. So if I have some quantity like this, which is a sort of an average, it's multilinear average over arithmetic progressions, is the way to think about it. So think of this as I'm taking configuration x plus h, x plus 2h, which are form an arithmetic progression, and then I'm taking my favorite functions, evaluating at them at those points, and taking the average. Then this is controlled by this sort of nonsense involving f0. So this inequality is true. And this nonsense involving f0 is what's conventionally called the Gowers U2 norm of f0. So this is just some expression, and we have a name for it. And again, if you want, you can think of this as the L4 norm of the Fourier transform. That's the same thing. So every talk should contain one proof, and I already proved something. So I will prove this, but the proof is just to actually know we've already proved it, basically. So the way you can do this is to sort of change variables. So rather than an xh average, I'll use an rt average, where r is sort of x plus h and t is x plus 2h, and then sort of encode f0 as this two-variable function. And then I can apply my previous Cauchy Schwarz argument to this to bound the left-hand side here in terms of some weird product of f's. And then if you sort of expand out the definition, that turns out to be exactly the right answer. Change variables again. So yeah, we've already done this one, but if you prefer, just Cauchy Schwarz out the f1 and f2s in the obvious way. Okay, and again, this is maybe not very fascinating. I mean, this isn't the part of the paper that everyone enjoys reading, but it is very useful. And it tells you really that the count of three-term arithmetic progressions, maybe you want to count three-term arithmetic progressions in some subset, and you know that this is sort of controlled by the U2 norm. So small errors in U2 norm will give you small errors in a number of arithmetic progressions. So okay, this is well known. This is fun. And again, if you want to object that I should have just done that using Fourier analysis because I'm not a Luddite, then that's true, but it goes wrong if you want to count sort of 4-term progressions or 5-term progressions. So a very similar result is true if I take this multilinear average over k-term progressions. This is controlled by the Gowers U k-1 norm. And the proof of this would be to sort of take this hypergraph thing that I didn't bother to write down and do the same thing as before, just Cauchy Schwarz out the a's and b's and the c's. Okay, so that also works. And again, this is very useful. If you want to control the count of 4-term arithmetic progressions in some set, this tells you that you don't have to worry about errors that are small in this Gowers U k-1 norm. And this is like a very central idea in Gauss's proof of some radius theorem and all of these other results. Okay. Cool. Any questions on that? I'm going very fast, but that's because I have a lot of slides. Okay, good. So far, I think this is all like none of these arguments have been very interesting. You just basically take the thing you have and you Cauchy Schwarz it, and then you get something. And by an amazing miracle, it turns out to be the thing you wanted. And so maybe these questions aren't terribly interesting, but I claim that's because we're looking at a very, very small portion of the problem space here, right? So what I'd encourage you to do is imagine just that you're doing your research, and in the course of your research, you discover it would be very helpful to know that like some multilinear expression involving some functions and some averaging is bounded above by some other multilinear expression involving some functions and some averaging and some products, maybe, with a small power here to make the inequality true. Yeah, maybe you want to prove this and you want to know whether it's true. And if it is true, can you prove it just by applying the Cauchy Schwarz inequality lots of times, like we've been doing that? That would be really useful. I think there was a time, yeah, like when I was doing my PhD or something, where I really thought that I would finish my research faster if I stopped what I was doing, wrote a computer program to answer this question, and then resumed doing my research, because somehow you feel that there must be a Cauchy Schwarz proof, but you can't see what it is, and you've sort of tried lots of things and you're not finding it. And this is a real bottleneck, right? So these problems come up a lot. Wouldn't it be great if there was some sort of way to just always say, well, yeah, we can do that. We can do it by applying Cauchy Schwarz. So unfortunately, this is where things get complicated. So I'm going to try and show you that the answer might be no, we don't know how to do that. So there's a question of Gowers and Wolf. This is this true complexity question. And essentially what it says is take any multilinear average over sort of linear configurations. So you can imagine this as being 3-term progressions or 4-term progressions or some other bunch of, function evaluated at x and y and x plus 2y and, some linear configurations, and you're averaging over these linear configurations. When is it true that this is bounded above by one of these Gowers norms, this Gowers US plus 1 norm, maybe raised to some small power? Well, specifically, they want to know, it's not too hard to show that this is true for some value of s here. Maybe you can put s as 100 or something, but they want to know like the smallest value of s, like, which one do you actually need? So for example, if you can do this with s as 1, then that tells you that your linear count is controlled by Fourier analysis. But maybe that's not true. Maybe you need s equals 2 and you need sort of quadratic Fourier analysis or something. So yeah, they were asking like, can you prove this inequality for the optimal value of s? Yeah, so there are sort of people who do dynamics and ergodic theory. So the corresponding question there would be to say, if I'm looking at these some sort of non-conventional ergodic average corresponding to this linear configuration, which Husserl factor do I need to control these averages? So you can show it's not too hard that some Husserl factor controls these averages, and you want to know the smallest one. Anyway, if you're not into dynamics, you don't have to worry about that, but that's basically the same question. So qualitatively, I mean, if you don't put this polynomial bound on the right-hand side, you just ask for something that tends to 0, right? Like if the right-hand side tends to 0, does the left-hand side tend to 0? Then this is known, and there's like a bunch of what, okay, at least for your favorite types of group. I mean, maybe not quite the generality I've written, but yeah, if you don't want this polynomial bound, then a bunch of papers show you that you can prove an inequality with the correct value of s, whatever that correct value of s is. Yeah, I won't go through these all, but Gowers and Wolf did a bunch of cases. Atami and Lovett basically killed off the finite field case, so when p is 7 and n is very large. Green and Tao did the case where n is 1 and p is a large prime, but then there was some sort of extra hypothesis about the linear forms that they needed that was removed by Altman. But essentially, this is qualitatively known. But it's notable that the proofs that are going on here are just sort of way different to the kinds of very easy proofs I've been showing you. So I mean, it's sort of irrelevant more or less to my talk how these proofs go, but I mean, to give you a very rough idea, they would say something like, well, okay, first show this is true with like u to the 100 or something, some very large norm, and then apply the inverse theorem for the u100 norm, and then you haven't even started really yet with the hard work. So then, like, do lots of hard work. You get to assume that fi is some sort of null sequence and see what you can say about it. But it's really long and it's really tough, and they do lots of hard work to make this happen. And it looks completely different from just like applying the Cauchy Schwarz inequality 10 times. Yeah, so maybe I'll just show some examples just to make it less abstract. So here are some instances of some inequalities that, I mean, I want to know, firstly, are they true? And secondly, can you prove them just by applying the Cauchy Schwarz inequality many times rather than using this high-tech machine? So the first one is, here's my favorite linear configuration. It's sort of, please count these linear configurations in 3 variables with, 6 functions. Is this count controlled by the U2 norm of F1? So in other words, is it controlled by Fourier analysis? And yeah, if you're an ergodic theorist, this is the simplest possible question I'm asking, is it controlled by the prime factor? That's what I want to know. Okay, it's a question. Second question would be, well, it looks very similar to the first question actually, but the only thing I've changed is these coefficients on the 6th form. So if I ask the same question but with different numbers, is it true now? That's something you might want to know. Let me ask one more, just that's not a Gowers-Wolf type question, just of like some inequality between some multilinear thing and some multilinear thing. Is it true? So if I take the U3 norm, which I've written out here, so this is some multilinear average over these Fs evaluated it. I mean, the way to think about this is an average over sort of these parallel pipets configurations. Then is it, so if I start with that on the left-hand side, is it true that that is bounded above by this sort of skew U3 norm, where if you look at it, what I've done is replaced all the A's on the first line with 13 A's and all the B's on the second line with 13 B's. This is a really random question that I basically made up, but it's actually going to be important for answering the first 2 questions, so I thought I'd write it down as well. But suppose this inequality had come up in your research, it looks like maybe you can prove it with Cauchy Schwarz. Can you actually prove it with Cauchy Schwarz? That's the question. So yeah, so maybe I should say, I think Gowers and Wolf sort of speculated that maybe the answer to some of these first questions was no. That was just a natural thing to wonder, right? So you can prove it using these very sophisticated techniques and the Husserl factors or Gowers norms and stuff. But maybe that's somehow necessary, right? And maybe we don't deserve to prove things like this. That's sort of intrinsically more complicated than you can prove just by like using the Cauchy Schwarz inequality lots of times. And they sort of speculated that maybe it's not even true with polynomial bounds, which would rule that out, right? So maybe the quality of the inequality should be sort of worse than polynomial here. So yeah, it's certainly not obvious just how to do some stuff until you've proven this inequality. Okay, so my goal is to try and prove these things. So yeah, I mean, the first problem is really where do you start, right? So all of the previous proofs were just like, well, take one thing and apply the Cauchy Schwarz inequality and see what you get and hope that a miracle happens. I mean, that's really not sustainable in problems of any scale. So sort of really, how are you going to guide the Cauchy Schwarz steps? Like, what's the principle behind it? And there's a way of thinking about this that, as far as I know, is I found it on a blog post on Terry Tao's blog. I mean, maybe it's sort of folklorish, but it's the only place I found it written down. So, for instance, take this thing that we already proved, right? This most basic Cauchy Schwarz argument. How should you think about this? Well, I mean, first instance, why is it true, right? Why would you expect this to be true? So the way you have to think about it is to say, well, look at the 100% case. Look at like the extremal case of this inequality, and then think about why that's true. So what this would say is that if the left-hand side is as big as it can possibly be, i.e. 1, right, because these functions are one-bounded and I'm taking an average, then this inequality implies that the right-hand side is also as big as it can possibly be, namely 1, right? And the largest number it can be is 1, and it's at least 1. So this is a consequence of this inequality. And the way to think about this is, well, I mean, for example, if this expression is 1, that means that the summand has to be 1 for every single choice of x, y, and y, and y prime, right? Because if this inside function failed to be 1 for even a single value, then it couldn't be 1 on average. So, okay, if you do that, and then you also sort of take the logarithm, so I can replace products with sums, then I get the following expression. If I have functions f twiddle and a twiddle and b twiddle, which I suppose now take values in the unit circle or something, and they obey this sort of functional equation that for all choices of x and y, this thing is equal to a constant, then f itself obeys this functional equation. So this is like a logical consequence of this inequality, and it corresponds to the 100% case. And this is also a true and fairly natural statement in its own right, I guess, right? I mean, suppose you're saying something that like a co-boundary is a co-cycle or something, if you really want to think about it that way. I mean, it's still pretty obvious how to prove it. You could just substitute in this expression for f involving a and b into this, and you get 0. But just for educational purposes, I mean, you could prove it in a very sort of nuts and boltsy way as follows. So here's an independent proof of this functional equation fact. So if it's the case that this hypothesis holds, I can rearrange it as follows. So f of x plus b of y is equal to c minus a of x. That's the same statement. And then I can notice that like the right-hand side here doesn't depend on y, right? It's only a function of x. And the left-hand side, well, if the right-hand side doesn't depend on y, then neither does the left-hand side, right? Because they're equal. And that means that the left-hand side for one value of y must be equal to the left-hand side for any other value of y. That's what it means not to depend on y. So for any two choices of y, the left-hand side is equal to itself with the other value of y. Okay, if I rearrange that, then I'll find that, take all the f's to one side. Then the right-hand side here, that doesn't depend on x now, it's just a function of y and y prime. And that means the left-hand side doesn't depend on x either. So the left-hand side for one value of x is equal to the left-hand side for any other value of x. And that gives you this statement, which conveniently is exactly what I was trying to prove. Okay, so this is an elementary proof of this bizarre fact about functional equations. And the reason I've written it down is that on closer inspection, this is exactly what the Cauchy Schwarz inequality proof is doing, right? Every time I do this duplication step where I sort of replace the left-hand side equals right-hand side by left-hand side equals other left-hand side, that is precisely one application of the Cauchy Schwarz inequality, and rearranging stuff is just rearranging stuff in both proofs. So this is the same proof in the special case. But sort of maybe it's easier to see what's going on in this proof, right? It's a nice algebraic statement. Okay, so if we apply the same logic to this arithmetic, like this three-term progression statement, for example, what does it say? Well, the 100% left-hand side is saying, suppose that I have these three functions and they obey this functional equation for any x and h, like when you add up f0, f1, f2 on an arithmetic progression, you get a constant. That's a functional equation that these functions might or might not satisfy, suppose they satisfy them. Then the conclusion is that f0 by itself obeys this functional equation. And if you look at it, like, this is exactly the same as saying that f0 is affine linear, right? I mean, it's sort of a constant plus a homomorphism or something. So this is a fairly natural statement. It says that in any solution to this functional equation, the function f0 must be an affine linear function. I mean, this is a sort of natural algebraic thing that if you cared about this functional equation for some reason, that you would really like to know. Okay, so yeah, so I guess this gives you a sort of a way that gives us this sort of dictionary between inequalities and these functional equation facts. And it maybe suggests a way you could try and prove these facts by sort of, first look at what's going on the functional equation side, and then try and take it into an inequality proof. So so under this dictionary, inequalities correspond to these facts about functional equations, like if this functional equation holds, then this functional equation holds. A Cauchy Schwarz proof here becomes this sort of elementary proof. I mean, by elementary, I sort of mean you could write it in first order logic or something, right? You can't do anything complicated. You can just add and subtract and change variables and stuff like that. And maybe we don't care so much about this, but the exponent, the number of times you have to apply Cauchy Schwarz, right? So the exponent goes down by a factor of half every time. That corresponds somehow to the length of this proof. So the longer your proof, then the more you have to pay for it. Which is not how we normally do mathematics, but it's true here. Okay, so what's the game plan? If I give you this inequality, it comes up in your research, and you want to know how to prove that left-hand side is the most right-hand side, what can you do? Well, you first write down the 100% version, the functional equation statement. That's just a statement about functional equations. You'd say, is it true? I mean, that's an important question, because if not, then you can stop, right? You get to go home early. Well, if it's true, then can you find this elementary proof, which is not completely obvious, right? I mean, maybe it's true for some highbrow reason, and this happens quite frequently, that maybe you know that f is a quadratic, and then later you see that it must be affine linear. But if you can really write down a nuts and bolts proof, then you can go away and turn that into a Cauchy Schwarz argument, and then you've proved your inequality, and you're happy. So this sort of gives you some sort of guiding principle behind coming up with your inequalities. There's a huge gaping problem with this, which is this last bit doesn't work. So it's the case that if you have a Cauchy Schwarz proof, that becomes a nice elementary first order proof. But the other way around, there's no reason to suppose that that would work, right? I mean, if I give you some nice first order argument, how do you set about figuring out that it looks like Cauchy Schwarz steps? Maybe it doesn't look like Cauchy Schwarz steps, and in that case, you're stuffed. So that's a problem. So okay, what does this look like on my examples? So here was my question 1, right? I have my favorite multilinear configuration in 3 variables and 6 forms, and I want to know if it's controlled by the U2 norm. So I apply my principle. I say, first of all, what is the functional equation statement? Well, it just says that if I have this functional equation, 6 functions, and they sum to constant on any of these x, y's, and z's, then f1 is affine linear. That will be the right-hand side. And this is a fair enough statement, and it's false. So that's great, right? You can just write down an example of a solution to this functional equation where f1 is quadratic, and that's not affine linear, and therefore the statement is false, and you don't have to prove anything. So this was really helpful, because I think we could have wasted a lot of time trying to prove this, and we don't have to. Okay. What about question 2? So this is where I have the same thing, but just with different coefficients on f6. So, well, again, there's a functional equation statement. It says if I have a solution to this functional equation, then f1 is affine linear. And this is now true. So I won't prove it, but you can go away, get out your algebra textbook, and it's so really this question of determining whether these facts about functional equations are true it's a sort of algebra problem, right? We shouldn't worry too much about this as analysts or anyone else. It's a statement in algebra. It's either true or it's not, and in this case you can check and it's true. Well, okay, so it's true, but can we find this elementary proof? I suppose this isn't really, I don't really know if this is a question in algebra or a question in logic. I mean, if you ask a logician, can they tell you when some statement like this must have an elementary proof that's just sort of first order? I don't know, I haven't asked one yet. It seems like a natural enough question, and I'm not going to worry about it either. So in this case, it turns out you just go away and you try very hard, and you sort of think about how to take your complicated proof and make it into a simple proof, and you succeed. And that's great. But then you try and turn it into a Cauchy Schwarz proof, and you're stuffed, because it doesn't look like a Cauchy Schwarz argument at all. So I succeeded in all the previous steps, but I still can't prove this inequality. So that's a problem. So just to give you some idea of what it might mean to say I have a proof that doesn't look like a Cauchy Schwarz proof. So Cauchy Schwarz proofs are incredibly special amongst arbitrary first order proofs. For example, if I'm proving something in this Cauchy Schwarz sort of strategy, the only way I can get line n is by applying the Cauchy Schwarz inequality to line n minus 1. Right? I mean, that's the only thing you can do. You can't suddenly start taking in normal proof, you can take line n minus 2 as well, and you can combine them somehow, but that's not how inequalities work, right? It's just like a chain of inequalities, and you can only really use the previous line. And so, yeah, if your inequality doesn't look like, if your proof doesn't look like that, then how are you meant to Cauchy Schwarzify? I mean, it's not sort of completely implausible. You could sort of combine, funnel it down somehow, but it's certainly not obvious. So just to give you an idea how bad that is, what that means is that if I can prove using a Cauchy Schwarz friendly argument, like one of these Cauchy Schwarz style proofs, that left-hand side, expression 1 is equal to expression 2, and I have another Cauchy Schwarz friendly argument that proves that expression 2 is equal to expression 3, that doesn't mean that I have a Cauchy Schwarz friendly argument that expression 1 is equal to expression 3, because I don't know how to combine two previous statements into one statement, right? That's beyond the abilities of the raw Cauchy Schwarz inequality. So this really is a horrible place in which to do mathematics, where like equality might not be transitive, and you somehow have to sort of find these proofs that work anyway. So this is a tough challenge to take a first order proof and make it nice, Cauchy Schwarz like. Okay. Oh, right, and just to round off, I had this third weird question, this like skew parallelepiped question. But this is quite instructive actually. So if I turn this into a functional equation statement, here's what it says. It says if I have a function f such that this thing is true, so whatever expression is equal to whatever expression, then this thing is true. Okay, and maybe that's not too insightful so far. But we can break this down a little bit. So if I take the second derivative of f, so second discrete derivative, right? So I sort of x minus x, f of x minus f of x plus a, and then I sort of do the same with a b. Then the hypothesis is really, and this is exactly this expression here, the hypothesis is that this doesn't depend on x, right? That this expression for one value of x is equal to the same expression for y. So that's really saying that as a function of a and b of the derivatives, this is well defined. Okay. And actually, we sort of know that functions whose second derivative is constant, that's really quadratic functions, right? I mean, sort of, I won't prove it to you, but that's sort of almost what quadratic means, is that take two derivatives, you get a constant function. And for example, if f was just alpha times x squared, then the second derivative would be 2 alpha ab, which doesn't depend on x. And what else do I know? So if I look at the second derivative, this GAB, the second derivative of a quadratic should be bilinear, right? It should be a bilinear function of a and b, which it is in this case. So maybe I can show that G is always bilinear under this hypothesis. So bilinear in this sense, right? That if I add stuff, I can split it up. And maybe, I mean, that should imply that G is bilinear in the other sense, right? You get the sense that if you multiply on the left, you can multiply on the right. And this is not automatic because this is just about addition and this is about multiplication, but you can deduce this multiplication step by just breaking up A13b into a whole bunch of GABs and then zipping them back up again. Sorry?
It's symmetric. It should be symmetric.
Oh yeah, it's symmetric. Yeah, right. It's symmetric by linear in A and B, but that doesn't help, right? I mean, it's still if A and B are both 1, then this is still about G13(1) and G113. So yeah, it's right. It's a good point. So yeah, we also know that G should be symmetric, but it doesn't help us here actually. So what I really want is this bilinearity by multiplication by scalars. But it follows in this instance from normal bilinearity if you just sort of unzip this to a whole bunch of GABs and then zip it back up again. And G13AB is equal to GA13B. That's exactly what this says, right? So this expression here is precisely G13AB, and this expression here is precisely GA13B. So the reason that I wrote down this inequality in the first place is because it corresponds to this sort of neat fact that if you're quadratic, then your second derivative is bilinear with respect to scalar multiplication. So it's a sort of natural fact. I mean, the inequality itself, maybe you don't care about, but the proof is actually fairly sort of enlightening. Okay, and then this isn't an elementary proof. I sort of skipped plenty of steps, but you can turn this into an elementary proof. That's not too hard. It's quite a long elementary proof, actually. So where this ... happens, as the number 13 tends to infinity, the number of steps will increase, right? I'm working at such a low level of proof here that I need multiple steps to prove that 13AB is equal to A13B. You need to unzip all the way. There's like 24 things in this ... So the proof will get pretty long, but okay, it's elementary. And again, I don't know how to turn this into a Cauchy Schwarz proof. So things where I say, for instance, apply bilinearity 24 times, it's not clear how to do that as a Cauchy Schwarz argument at all. Okay. So what can we hope for? So I mean, things went pretty badly, right? I had this idea of how to prove things by Cauchy Schwarz, and then it didn't work because my elementary proofs don't look like Cauchy Schwarz arguments. But the dream is that maybe you can do it anyway. So wouldn't it be great if I take my inequality, I turn it into a functional equation, like I see whether it has an elementary proof, and it does have an elementary proof. You know, I've asked my algebraist and I've asked my logician, and they both come back, you know, it's good. That now somehow maybe there should be some way of taking that elementary proof and massaging it until it looks like a Cauchy Schwarz proof. I think this would be like really great because me in my PhD would have been very happy about it, right? I could have saved a lot of time, get my computer to run these arguments, and then I know that things are true by Cauchy Schwarz. I think that'd be like a lovely thing to be true. Alternatively, because you should always play both sides, wouldn't it be interesting if this was false? So this would tell you that some inequalities are sort of elementary and they can be proved just in this very hands-on way, but other ones are sort of intrinsically complicated and they can't, you know, there's something harder about their proofs of these elementary statements that resists being Cauchy Schwarzified. And then there's some sort of hierarchy of inequalities depending on how complicated a technique you need. I think that would also be interesting. I mean, you know, say, yeah, if you're working in this, that would tell you that sort of Cauchy Schwarz logic can prove fewer things than classical logic or something. I don't know. I'm not a logician, so I won't try and make that precise, but I think it would also be interesting. So that's the dream. What can I actually tell you? So I can't prove this. I can't prove, I'd love to, but I can't prove that anything that you might be able to prove using Cauchy Schwarz, you can prove using Cauchy Schwarz. But my sales pitch is that I can do this like by hand, by dint of sheer effort, in a number of quite interesting cases. So yeah, there's a bunch of instances of problems that in fact, all the problems I've written up on the screen, basically, I can actually make this happen. I just have to work really hard. And the thing I have to work really hard at is taking this arbitrary proof and massaging it until it looks like a Cauchy Schwarz proof. I don't have a generic way of doing it, but I can do it by hand. Okay, so for example, this sort of silly skew U3 inequality, this is actually true. I can prove this. That the U3 norm is bounded above by the skew U3 norm, and actually just to sort of, you know, what the hell, that the exponent I get here, this 1 over c is like log k, which is actually the basically best possible up to constants. So so yeah, it's not only is my proof possible in principle, but it's also very efficient. Okay, and for this Gowers Wolf question, so remember they wanted to know that this multilinear thing is bounded above by the US plus 1 norm for the smallest possible s. So if you run that through our machine, you say like, what's the best s which this could possibly be true? You know, when is the corresponding functional equation statement true? When is it true that, you know, any solution to this functional equation is like polynomial of degree s or something in fi? Well, you do the algebra, you go talk to your algebraist, and they tell you that this happens precisely when the s plus first tensor power of this linear form isn't in the span of the s plus first powers of these other linear forms. I mean, it's whatever it is. I mean, I don't want to go into that right now. Okay, so I can't quite prove it all the time, but the question that was actually posed by Gowers and Wolf originally was asking something slightly stronger, saying if these are linearly independent, then this inequality holds. So there's some corner case where they're not all linearly independent, but this one is linearly independent of the others, which I can't do, but yeah, the case they originally asked about is when they're all linearly independent, or you can put any I on the right-hand side here. And that one I can prove, and again, this constancy is not reasonable. And moreover, this proof is just by iterating Cauchy Schwarz. There's no inverse theorems, there's no high-tech machinery, you just sort of work through it. Okay, it's a natural pause point. Anyone have any questions? Yes.
Are there any instances where you could like prove the other way around?
How do you mean the other way around?
Like the fi norm.
Oh, it's bounded above by this expression.
By something.
Something of this form or something?
Yeah,
it's a good question. It's like an anti-Gowers Wolf question. Yeah. I have thought about it. I don't know. I think it's delicate. So yeah, I'm going to talk about it later. I think there's maybe cases of it I can prove, and I think there's cases of it that I want to prove that maybe I know I can't prove because the corresponding functional equation statement is true but doesn't have an elementary proof. So it sort of fails at the previous step of the game. But in many cases should be true, and I haven't thought too hard about how to prove them, but it would certainly be something amenable to these techniques. Yeah.
Can you say more about where this constant c comes from? It's not just scaling, right?
No, so this constant C is like how many times do I have to apply Cauchy Schwarz? Right, I mean, I start with the left-hand side. Every time I apply Cauchy Schwarz, this constant C goes down by a factor of 2.
Sure, but how's it related to S?
Oh, how's it related to, oh, I see, yeah. So what I can guess is something like C is, what is it? It's like log of the coefficient size of the linear forms raised to some constant depending on S and K, which is the two unreasonable. It's like S squared times K cubed or something. Yeah, it's sort of explicit, but not, it's not quite optimal. I probably expect it to be log K plus some constant, but yeah, it's theoretically nice. If you actually had to get this bound out and use it in the real world, then obviously it's just like less than the number of atoms in the universe or something. But yeah, it's a reasonably explicit function of yeah, a function of the inputs. You do care about the coefficient size, that is important. Sort of for the same reason that when I multiply by 13, the number of steps I needed depended on the number 13. So if you're working over finite fields, you can just set the coefficient size to be t, but in general, you need to care about the coefficient. Yeah. Yeah, question. Any question? Yeah.
So you had this other constant A that appeared, like this is earlier, like when you were setting up functional equation.
Yeah.
But are those 0 because the one side you take logs and they're both equal to 1?
So there was something, I'm not sure if I'm going to be able to.
And it also seemed like when you were going through the proof that what the constant was didn't matter in the proof. It just like went away.
Yeah, absolutely. So this constant C right here.
I think page was A.
This is just because there's an absolute value sign around this expectation. So if I scale any one of F1 through F6 by an arbitrary multiplicative constant, then it doesn't change the left-hand side. And when you take logarithms, that's just saying that the sum is not necessarily 0, it's a constant. Yeah, I mean, you can get rid of this very easily just by rescaling, absolutely.
Okay.
For the right-hand side, I know that the constant is 0 because it's a positive real number or something. But yeah, this is just an artifact of the fact that I put absolute value signs here rather.
Okay.
Yeah. Cool.
Yeah. Question. Do you know when you cannot do something by iterated Cauchy Schwarz?
Do I know of instances where I can't?
Well, how do you know that? How would you know that?
I have no idea. So, so one thing that can go wrong is that I can't find the statement might be false. It might be that it's true, but I can't find an elementary proof. And that I think can happen. I haven't written down in the literature about this, but I mean, the person to talk to is, sorry, it's gone on my head. But yeah, there's sort of things like if it's sensitive to the choice of coefficient ring or something, then you're in trouble basically. So that could happen. But if I have an elementary proof written down in front of me, then I have no idea. I have no idea like what would the instruction would be. I mean, I think that's a great question, but I have nothing to say. Yeah. Okay, cool. Let me crack on and see what I can do in the next minutes or something then. Cool. So okay, so my next goal is to tell you at least something about how I can do this, how I can apply these Cauchy Schwarz arguments lots and lots of times. So the very first thing I have to worry about is a sort of silly thing, but it's just notation. So, I mean, it really is the case that I would take one of these, F1 up to F6s, and I might have to apply the Cauchy Schwarz inequality to it, like, 20 times or something. And I now have 1 million forms in like 1 million variables, and like, they're sort of all over the place. The structure is very complicated. If I try to write that on a piece of paper, I'm going to run out of pieces of paper. So I just can't write everything explicitly. It's hopeless. If you try and go down that route, you just drive yourself mad. So we need some other formalism for talking about what's going on when we apply Cauchy Schwarz a bunch of times that's more sophisticated than just writing the equations. So here's how I want to think about this. So suppose I care about this multilinear average, f of x plus y, a of x, b of y. I'm going to think of that as like a diagram. So by diagram, I could mean diagram in the sense of category theory, but you don't have to be fancy if you don't want to. But I just mean, yeah, so like here's x and y, that's like a copy of fp squared. This is a linear map that sends xy to x plus y. Here's one that sends xy to x, and here's one that sends xy to y. And on each of these green nodes, there's one of these functions. So f lives on here, and a lives on here, and b lives on here. And this is just like a schematic drawing of this multilinear average where I've sort of ignored what the functions are. Green, by the way, like I call these leaves. So any vertex that actually has a function living on it is called a leaf, and leaves are green. Cool. So yeah, and if I want, I might write the coordinate version in the boxes rather than FP squared. So this means the same as this, it's just I've actually written the maps out explicitly. Okay, so that's very useful. What does it look like to do Cauchy Schwarz in this framework? So suppose here's an example of a Cauchy Schwarz argument. I start off with this thing on the left-hand side and I Cauchy Schwarz out B, right? And then I get some rubbish. So what does that look like? Well, it turns out that's the same as saying take two copies of this diagram and join them together, where the place I join them together is the thing I Cauchy Schwarz out. So in this case, it would be B of Y, and I've gotten rid of B of Y here. So what happens, so this vertex stops being green because I've gotten rid of B, it's no longer in the picture. And these two copies, that means like, two copies of this whole variable set up and this whole variable set up, but with the condition that they have to be equal on the overlap here, where they join up. So if you want to be fancy and a category theorist, you say that what I'm defining is the limit of this diagram, right? Or the fiber product, if you want. So just take the fiber product of this and this joined at this variable y. That's what x1, x2, y really is. And the great thing about this is that you don't have to get into coordinates to say what it is, right? I mean, the nightmare of applying Cauchy Schwarz is that you keep having to change variables to apply your next Cauchy Schwarz stack. Here I can just say, this is the fiber product of these two things over this, and that's what you're averaging over. So this saves you an awful lot of pain. And then I can carry on. So if I have this diagram and then I apply Cauchy Schwarz in these next two, these x's, these A of x's, I get some diagram that looks like this. And these diagrams will rapidly become complicated, but it's sort of okay. Okay, so and then the functions left over would be on these four vertices. Okay, so that's, yeah, so Cauchy Schwarzing means duplicate your entire diagram, take two copies and join them on the things that you Cauchy Schwarz out. Okay. What else? Oh yeah, and I can forget about the coefficients if I want. The choice of basis is not important. You can do this in the abstract.
Sorry,
Yeah,
in those diagrams there, we've lost some information, right? Because now the functions on the bottom diagram on the left-hand side, the two green boxes, these are somehow the same functions.
Yeah, so it's a good point. So yeah, these functions here, actually all four copies of these are the same function.
They're all the same, but you lose that information.
Yeah. So excellent point. So there are two things. So one is that it turns out to be very difficult to use that information all of the time. I mean, because maybe you could get some sort of positivity or something if you knew they were the same function, but in practice, if all you're doing is Cauchy Schwarz, that information is actually never used, right? It's just until the very end where you look back and say, okay, it turns out all of these functions were the same function, so I get to apply the, yeah, and in reality, I'm gonna, if you read the paper this is based on, then I also keep track of some doohickeys to sort of tell you which function is present in the vertex, and there's some sort of extra bookkeeping going on there for that reason, but it doesn't play much of a role in the arguments. Yeah.
Okay,
Thanks. Yeah. Okay. So what else are we going to do? So I'm not a complete sort of monomaniac. As well as the Cauchy Schwarz inequality, I'm allowed to use other inequalities, and a useful one is the triangle inequality, so that this is not too deep. So here's an example of applying the triangle inequality. If I have this multilinear average, which is the U2 norm, then I know that it's bounded above by this multilinear average, at least for some choice of F2 and F3. Then I don't really care what it is. So just like you're saying, if I stop caring about what functions are, then I have more flexibility. So why is this true? Well, essentially I can do a change of variables. So I can say X is going to be Y plus Z, and A is going to be negative Z, and B is going to be negative Y, okay, plus some other variable T that I don't care about so much. When I apply this change of variables, this is what I get. So I have F1 of Y plus Z, F1 of Y, F1 of Z plus T, and F1 of T. And then by the triangle inequality, I mean, like, if I don't care about T, I can just remove it, right, by the triangle inequality. So pull out F1 of T, take this average over T, and this is bounded above by what I have inside the average. And then I can always pick a particular T, like pick one T that makes this right-hand side large, and then set like F2 to be this, and F3 to be this, and then this is exactly the thing I wanted on the right-hand side. So what I want to take away from this is that I can secretly like specialize these variables to be any other variable. So I can use fewer variables, Y, Z, and that's it, in place of 3 variables here. And I get the right-hand side being the left-hand side, but specialized to this choice of X, A, and B in terms of fewer variables. And then by the triangle inequality, as long as I'm willing to like accept translates and stuff, then I can just average out any of the additional averaging here that I'm not really using. So okay, this is like what I call specialization. It's true of the triangle inequality. And you could draw it like this, I suppose. So here's a picture, a diagram of the left-hand side. Here's a picture of the diagram of the right-hand side, and I've just substituted in these coordinates for x, a, and b, and this is what I get. And here you notice there's a 0, and 0 is like not interesting, so I can just remove that. And that's really my f1 of t that's being averaged out. Okay, and if you want to be fancy, you can say this is a morphism of diagrams between this diagram and this diagram, but let's not go there. Okay, 2 more quick things that I need. So I also observe that I can merge things. So if I start off with this diagram on the left and then I specialize it to this choice of coordinates, then I now have a z and a 2z. And it's not a deep statement that if I have a function, f2 of minus z times f3 of 2z, this is some function of z, right? Like I can just notice that this is a function of z, and in doing so, merge these 2 functions into a single function, which is just a function of z. But that's not deep. And the last thing, which is sort of super important, is that, so how do these complicated diagrams that I built up interact with the triangle inequality? So imagine that I built up some vast, horrible diagram with intersections and stuff, and it's a huge fiber product with thousands of variables. And then I want to specialize it to like 2 coordinates, like x and y. I'm just going to sort of specialize everything to be some linear functions of x and y. And what I need to check is that that was a valid specialization, right? I mean, it needs to be a valid change of variables, otherwise it's just not true. So how do I do that? Well, suppose I start out with this and I apply Cauchy Schwarz, and now I have 2 copies of it joined in the middle. If I have a specialization of the left-hand side in terms of some one parameter t, say, so I'm going to set x, a, and b all to be some functions of t. And I also have a specialization of the right-hand side in terms of some different functions of t, and they agree in the middle, then I can specialize the whole diagram just by gluing them together. So if you want, this is like the universal property of the fiber product or something, but it basically says if I'm writing numbers in these boxes to sort of specialize all these parameters, then as long as I check it locally and it patches together, then it's true everywhere. So this is amazingly useful because I'm going to build this colossal diagram with like thousands and thousands of variables, and then at the end say, okay, but I actually only needed an average over 2 variables. Here's how I'm going to specialize it. And you can just like look at this diagram and see that that's a valid specialization without having to sort of explicitly compute matrices with size 10,000 or something and check it that way. Okay, so how am I doing? Not very well. I have very little time. So I was going to give a sketch of this bilinear theorem, this sort of weird multiplication by 13 thing for arbitrary k in terms of these diagrams. So I need to go through this a little quickly. But okay, the left-hand side is this U3 norm thing. And I could write this as a diagram like this, right? I have some x's and a's and b's, and these are exactly the linear forms that I had up before. And my strategy is going to be start with this, do lots of Cauchy Schwarzing, do lots of specialization, and then hope that I get something at the end that looks like the right-hand side. And specifically, actually, so it turns out what I want to do is this. So if I can do lots of Cauchy Schwarzing and specialization or whatever and get some vast diagram which has this general form. So here is like 1 copy of r plus kt. So rt are variables and k is like 13 or something. And I also have another form here, which is 13r plus t. And then I'm allowed a bunch of r's and t's in the middle, and that's it. If I can construct something like this, well, when I translate that into some inequality, then that's saying that f u3 is bounded above by some linear multilinear average that looks like this. And then I apply Cauchy Schwarz 2 more times to get rid of a and b, and then that turns out to be exactly what I want to do. So in the sketch I had earlier, it's like instead of differentiating f twice at the start, I want to differentiate f twice at the end or something. But whatever. That's hopefully, why would I lie to you? If I ever find a diagram that looks like this, then I promise you I've won and I can go out. Okay, so that's my first idea. The second thing. So maybe this counts as sort of premature optimization, but remember I said that a crucial part of the original proof, the first order proof, was to show that f of 13ab is equal to, sorry, g of 13ab is equal to g of a13b or something. So I said you could just expand it all out and then zip it back together again, but that's kind of inefficient, right? This is sort of like multiplying by 13 by adding things in unary like 13 times. If you care about the number of steps, you can actually make it logarithmic in 13 rather than linear in 13. And how does that go? Well, it's sort of some double and add argument, right? So you say, well, 13 is odd, so I can split off AB, and then there's 12 left over, and then 12 is even, so I can split it as 2 6s, and then I can group those together again in the B variable. Okay, and 6 is even, so I can split it as 2 3s, and then I sort of group those together again. Okay, now 3 is odd, so I have to split off an A, but then I can like absorb it back into the AB I had at the beginning, so now I have an A5B. And now 2 is even, so I can split the A's off and then, group them back together again, and then finally merge bac on the A's, and I get GA13B. So there's this sort of, it's really a sort of binary multiplier thing that means that I can write a proof that G13AB is equal to GA13B that's logarithmic in length rather than linear in length. But I also find it kind of helpful to think about this way. So this is sort of, more enlightening than the silly elementary proof. Because this sort of shows you that you're really sort of doing a computation here, right? Sort of, I'm building a proof called how do I multiply by 13? And one way you can think about it is in terms of some sort of circuit, right? Like imagine I have a primitive computer and I'm trying to teach it how to multiply by 13. Then I would do some sort of thing like this. So B comes in on the left and then it goes up to this top rail. And then I split it and add, and that sort of doubles it. And then I keep doubling it and doubling it. And then at the binary digits of 13, where there's a 1, I sort of tap down a copy of 4B and I add it together and I accumulate. And then I eventually multiply by 13. And this is exactly what the proof does if you look at the B variable. If you look at the A variable, it's sort of the opposite way around. So A comes in from the right, and then it's sort of you keep on doubling and adding A until you get 13. So and weirdly, these diagrams are sort of dual to each other. Every time you have an equals here, you have a plus here, and vice versa. And that's really because otherwise we wouldn't be proving something about bilinear functions, right? That sort of whenever you add in the first argument, it must be equal in the second argument. So anyway, so I think about this bilinear argument as really saying, build me this computer that multiplies by 13. Okay, so having said that, so maybe I'll skip over this a little bit. So this is my starting diagram. This is a copy of the U3 norm. I'm ultimately going to want to specialize lots of copies of this. This is the building block that I'm going to build this huge diagram out of. And then I have to sort of pare it back and say, okay, give me a function in 2 variables. So ways you can specialize this. Well, one thing you can do, which I call sort of plus, is where you take 4 things here that happen to add to 0. So 100 plus 123 is equal to 103 plus 120. So the sort of alternating sum of this is 0. And then I just let the right-hand side be the same thing. That's a valid specialization of this picture, right? You set x, y, a, b to be some numbers. Another thing you could do is set a and b to be 0, and then this is some number, and these are all 0. That's another valid specialization, right? Set y to be 0 as well or something. And then you can sort of add together one of one and one of the other. That's also a valid specialization. And I like things like this because then I get to merge these 4 things together because they're just functions of u. So you'd end up with something that looks like this. Sorry, this is maybe too fast to be helpful. And I'll draw this picture to represent something that looks like this because I don't have space to draw all of it. So here it goes. This is the grand proof when k is, so this is multiplying by 3. I can't do 13 on the slide, that's too big. But here it goes. So I'm going to start with my original diagram. I apply Cauchy Schwarz to get 2 copies. I apply Cauchy Schwarz again to get another 2 copies. I now apply Cauchy Schwarz on all 3 of these things in the middle to get 2 copies joined in the middle. And now I specialize in the following way. So each of these is really, has some variables associated to it. And I specialize them to be functions of r and t, which are my 2 new variables. And if you look at this, there's an r plus 3t here and a 3r plus t here, and everything else is either an r or a t. And so, as I promised you, I now get to go home. Yeah, this is 2 more Cauchy Schwarzes, and this is a proof, at least for k equals 3. What the heck are you looking at here? So I think it's helpful to split this apart to look at just the t's and just the r's separately, and then add them together later. And this is exactly a binary multiplier for multiplying by 3. So if you look at the r picture down here, an r comes in from the left, I take it up to the top rail, I double it, I add them together, and then I sort of add the 2r down again, and that's how you compute 3r, because 3r has 2 binary digits, 1 and 1. And similarly, t is the same going the other direction. So really what I've done is I've built that arithmetic circuit that I was talking about using these widgets that are the sort of the original diagram that I started with, and then you get this complicated picture. Okay, when k is bigger than 3, I'm going to need a binary multiplier with more stages. So you just sort of take this picture that I built up, and then you sort of apply Cauchy Schwarz again to double its length, and you get something like this. And then you specialize it, and you can think of this as being the first one of these binary multiplier gates, and this has been the second one. And a number would come in here and it would get doubled, and you tap down, and then you can multiply by 7. So that's how you multiply by 7. And then if you multiply by larger numbers, then you just sort of keep applying Cauchy Schwarz, and you double the number of blocks every time. The circuit gets longer and longer and longer. It gets twice as long at every step. So because I need one block to do one bit of binary multiplication, if I need like log base 2 of k blocks overall, and because the number of blocks doubles at every step, that means I need like log k Cauchy Schwarz steps plus of 1. And that's why I get the log k control at the end. Okay, so some things that are true. So interesting fact about this, by the way, is you get to build the circuit without knowing what k is. And then when someone tells you k, you sort of specialize it until it multiplies by k rather than by some other number of size k. So this turns out to be very important, that the circuit is amazingly flexible. It does all of the computations I want using just one computer. And yeah, so, and it's very symmetric. So if you think about it, any circuit you build up by just applying Cauchy Schwarz is going to have a huge amount of symmetry, right? Because you keep on just duplicating it. So, but then you get to sort of break the symmetry at the end by sort of programming it with choosing the specialization carefully. Okay, it's not clear how that works, but I promise it's true. And you can generalize this to multilinear algebra because, rather than bilinear algebra, you just have sort of, rather than R and T, you'd have like R and T and U, and then you sort of, I promise it generalizes in the way you want. So if you want to prove like theorem, problem 1, whatever it is, this Gowers Wolf type problem, here is like not even a sketch of how this goes. You write down a proof, and the proof kind of basically reduces to multilinear algebra, or to bilinear algebra. So really, you look at the second derivative of f, and it's not too hard to show that that's well defined, independent of x. But you really want to show it 0 because then you'd be affine linear. And so you have a proof that the second derivative of f is 0, which uses sort of second derivatives of these other functions in multilinear algebra. There's some big computation. Along the way, you might have to like use this bilinearity fact that if you multiply by 13 on the left, you can turn it into multiply by 13 on the right. And it's very complicated, and then you sort of turn it into this really big circuit. And here's a picture of the really big circuit that you need. Just to give you some idea of what this is like, each of these little things here with an A written on it, that is shorthand for one of these diagrams, possibly with an unlimited number of blocks. So, I mean, I'd ultimately have to convince you that this big circuit, not only can I build it using the Cauchy Schwarz inequality many, many times, starting out with some like little left-hand side configuration, I can also then specialize it to sort of prove that something is controlled by the U2 norm. If you really want to go through that process, read the paper. Okay, and I'm sort of out of time, but let me say incredibly briefly. So yeah, I have to build these things by hand. I would love not to have to do that. If you can figure out a way to build them not by hand, then please let me know. That'd be great. If you want an example of something I can't do this way, but maybe you could, it's not impossible. Like I said, I can sort of do Gowers Wolf only in this sort of symmetric case where all these things are linearly independent. If some of them are linearly dependent, but not the one I care about, then it should still be true, but somehow my method breaks down. So I don't know whether that's a fundamental obstruction or whether I'm just not clever enough to write down the right circuit, but it seems to be difficult. Okay, final thing, if you don't believe this dream of mine, that maybe you can just take any elementary proof and turn it into an inequality using Cauchy Schwarz and stuff and the triangle inequality, well, you could always just try and give yourself more tools, right? Like other inequalities exist, you could try using those too. Some of them just don't seem to help, but one of the things that might help is if you let yourself kind of use the regularity limit. So there's this precedent is this work of Tau and Ziegler on concatenation, where it's sort of, they have tools that I can't do and seem like they would be helpful. But the expense is you don't get good bounds, but I mean, maybe you don't care about that. So at least you'd have a qualitative result. Yeah, as I say, if the dream is false, that would also be very interesting for me. Maybe less useful, but interesting. Okay, I think that's all I have, and I'm out of time, so I should stop.
Can you go back a couple slides?
Try. How many slides?
Maybe one more. Yeah, right there.
Yeah.
So for some problems that you might want to say replace the x or y's or z's, so say like x squared or y squared or x times y, is that something your method can handle at all?
It's a great question. maybe. Yeah, I always think that this sort of thing should be, and if you can come up with some sort of proof in the 100% case that, you know, like some polynomial is independent from some other polynomials, maybe this should go through. Seems very plausible. Every time I actually try and do it, it seems to be more complicated than I hoped. But it's certainly something you could try. I mean, you're going to run into problems, but maybe not problems that you can't solve. I mean, somehow this big diagram, it's really helpful to know that all the maps are linear. And if you suddenly start finding that they're polynomial, then it's going to be tough. But I mean, it's plausible. Yeah, I mean, that would be a great example of a wider class of problem where you might hope these methods apply and could prove interesting things. And I can't even know how to do it. I think also Sarah sort of proved all of the low-hanging fruit in that this method might apply to anyway. So if things are independent, if the polynomials are independent, then Sarah can already prove it. So there's no prize there. So you'd have to do cases where they're not independent, and it gets pretty messy pretty quickly. So yeah, yeah.
So this is all for some finite group G, right?
Yeah.
Suppose I care about, say, things in ergodic theory, then usually you have actions of the whole integers, and then do all these methods kind of just carry over? Or?
That's a good question. I thought a little bit about this. You end up with technicalities that I think are sort of well understood. And it's basically about the fact that changing variables over the integers, I mean, you know, if x is ranging over the interval 1 up to n and y is ranging over the interval 1 up to n, then x plus y doesn't also range over the interval 1 up to n. It's a more complicated distribution.
But that's usually not a big deal.
It's usually not a big deal. Yeah, I think sort of if you could throw Gaussians at it or something. I mean, like you could do something like that and then have to keep track of lots of extra parameters of like how much you've had to squash in order to make the inequality true. I think it should work. I haven't tried, it was sort of bad enough, but I guess the good thing is that if you proved a couple of key lemmas worked in the integer setting, then after that everything is sort of basically a machine. So you wouldn't have to do it all the time. But yeah, that's good. Yeah.
Do you somehow keep track of let's say complexity of these linear configurations in order to ensure that at the end you end up with the Gowers when you do this whole nationally? Or?
Oh right. Yeah, I see. So right, so it's certainly, so one thing that you might be tempted to think about is like, so you can suddenly lose this game, right? You can keep taking Cauchy Schwarz and end up with a configuration which has the wrong complexity, and then there's just no possible way that you can get back. So yeah, you might imagine having a little safety mechanism sitting on top of your argument that sort of a big light goes off if it turns out that you now have the wrong complexity. I don't have to do that explicitly because basically I'm sort of following a proof strategy in my head that I know in advance is going to work. And then once it's all written down, then, so there is another thing about the proof that there is an inductive component to it where in order to get down from complexity 10 to complexity 2 or something, I have to do it iteratively. And there I would, I guess you could say I'm reducing the complexity by 1 every time. Yeah, but I don't need a number just because I have meta reasons for believing that the complexity is the correct thing. Does that make sense, or is that not?
Actually, when I meant complexity, I meant something more like, for instance, when you do the pad induction scheme in Nelson-Reddy theorem, then you start with some polynomial average, and after doing Cauchy Schwarz or rather output, you end up with a configuration which is, in some sense, it has lower type or lower complexity, whatever you call it.
Mm-hmm.
So somehow, what I'm interested in is whether you, when you do your Cauchy Schwarz here, whether there is also some sense in which your configuration has lower.
I think the answer is I don't think so. So if you look at something like this particular linear configuration with the stuff, like whether this is even going to work depends on the coefficients 2, 3, and 6, which is like a very sharp. So I mean, in fact, for the generic choices of coefficients, you somehow, I suppose it works for generic choice, but like somehow you have to hit something on the nose. You have to find an identity amongst these coefficients, which is satisfied, which means that the whole argument deserves to go through. If you sort of miss by even a tiny bit, you're not doing the right thing. So the proof doesn't have the flavor of like making things simpler and simpler and simpler. It has the flavor of building a giant calculation which proves exactly the thing you want to know, And then once you've done that, then you're done. So I think it's a different flavor to the PET schema. It's it's sort of the PET schema is like I can just recursively make progress, and there is no progress. Like nothing is proven until everything is proved. If that makes sense.
So how do you realize at the end that you look at this big diagram and you realize, wow, it's the Gowers?
Basically just like insane linear algebra, right? So you build this massive diagram and then you specialize it to like 2 parameters R and T, and then you apply Cauchy Schwarz a single extra time, and then you have the U2 norm. But to verify that the specialization was correct is like awful. So yeah, that's really where the hard work is. Right, way over time, so.
I have a question.
Oh, wait.
Can you do like multidimensional stuff? Like if I give you something that is like not obviously controlled by the like 2-dimensional box norm,
yeah,
but like by a change of variables, but secretly is, can you?
I know of no reason why not. If you have such a problem, I can try. I have no guarantee that I will succeed, but I know of no obstruction. So yeah, there's nothing about this needs to know that you're one-dimensional. Like in the intermediate stages of this calculation, you can have like vast dimensional things coming up. So
more questions? Okay, if not, let's thank Freddie again for a great talk.